Hey folks, this is not a quick video. It's going to be a video with two examples of how to use technology to solve an application involving polynomial functions. Okay, we're not going to be graphing this by hand. We're going to use Desmos, which is a great graphing calculator. It looks like this. We're going to use that to deal with this question, okay, to help us. So it says in an auto shop there's an engine hoist. This hoist is a metal beam with a chain in the middle that hooks on and lifts an engine out of a car. The metal beam is strong, I imagine, but it does bend slightly because an engine is heavy. No kidding. Here's a formula that models the situation. D is the amount the beam sags or bends in centimeters, and x is going to be the number of meters from the end of the beam. So it's a very big beam, okay? What we're going to do, and by the way, we did something called function notation. We did a video on that recently. Right there is function notation, okay? That's function notation when you see it like that. But this is the part we're going to graph. And instead of function notation in Desmos, I'm just going to put a, I don't know, like a y here. Okay, y equals, and then all of this. So I'm going to type this in right now with you. So we're going to start with y equals, and this is Desmos at desmos.com/calculator. And I'm going to go 1, then hit the divided button and put, was it 800 or 1800? I'm going to have to flip back and forth. It's 1800. And then in brackets, let's see what they had there. 950x, 950x, starting to graph for us, but that's not what we want more here, minus 22x cubed, minus 22x, and to do a cubed, right down here, you hit the button that looks like with the a with the exponent b. But we want a little, we push that and then we want a little 3 there. Now the graph's looking really cool. I'm going to hit the arrow key to the right to get back to regular typing again. And we want plus x to the power of 4, or x exponent 4. So plus x, and then hit that a to the power of b, or a exponent b button. X, so we get x exponent 4. Then I'm going to hit the arrow to the right and put a bracket on the end. Okay, now we have a graph of this situation. I think I'm going to make the graph a little bit thicker, so I'll put it in projector mode. Now that I have typed this in correctly, I'm actually going to move this off the page just so we can see the graph better. Isn't that nice? By the way, with Desmos you can change the look of something by hitting this little edit button here. You can change the color of the graph, etc. If you like green better, there's nothing wrong with that. It's actually a color I really like. There we go. So let's go through some of these questions using this graph to help us. Number 1, graph this function using technology. Wow, I should have read that earlier because I just finished doing that. Check. I'm going to go to the next page here. Now it says, try to figure out the domain of this function, where d and x model the relationship between the sag and the number of meters of the engine from the end of the beam. In other words, they want us to be realistic about our domain, okay? Now this is assuming that you've already done domain before with me on a video or with your teacher, okay? If you haven't, it's definitely important to check out the video on domain and range, okay? So first of all, we start by writing d, and we're going to be talking about the x values. Okay, x is an element of the real number system such that, and now is where we put our restrictions on what the domain will be. Okay, let's look at our graph. Here it is. By the way, the beam, let's see, let's go back to this for a second. The x, it says where d and x model the relationship between the sag and the number of meters of the engine from the end of the beam. Okay, well, we're dealing with positive numbers here, so we're going to be dealing with numbers between 0 and, so it sags and I suppose somewhere around here, whatever that happens to be. In fact, I can touch that spot. I can see it's 8.3. Okay? But anyway, we want to talk about the domain between the spots where that beam sags. So if there's no weight on the beam, we're right here. Okay? And as the engine is heavier, here's the amount that the beam is sagging. It looks like it's sagging quite a bit actually, but remember this 1.489 is talking about centimeters, and over here I think is 4 meters. Wow, that's really quite long. And then you keep going until it doesn't sag anymore, which is at 8.3 when there's no engine on there, basically. Okay, so the domain is between 0 and 8.3. Okay, so we go back to our thing here and we write x is greater than or equal to 0 and x is less than or equal to 8.3. That is the domain of this situation. Okay, so hopefully that is good enough for the domain. Now again, it's going to be confusing if you haven't watched the other video. Next question. What is the maximum this beam will sag or bend? Well, if we look back at this question here, we can see that the maximum sagging point is right here. Okay, and it's going to sag this far, which is 1.489. I'm just going to round it off to 1.5. Okay, it's going to sag 1.5. And by the way, let's check and see. The amount that it sags is in centimeters, okay? And the x value is the number of meters. It's a huge beam, obviously, in this case. I'm not even sure if this is realistic. Sometimes in math, the questions aren't totally realistic. I don't know if the beam would be that long for real. But anyway, we can see that the beam would sag about 1.5 centimeters. Okay, so let's write that in. How much will it sag? It will sag 1.5 centimeters maximum. Okay? How much would the beam sag if the weight was 2 meters from the end? 2 meters. Okay, let's go back to Desmos here. At 2 meters, right here, the beam would sag. In fact, we can drag this point along here. Pretty nice, eh? At 2 meters, there we go. It's 0.967. Wow. I'm going to have to round that off to 0.97 centimeters because it's not quite 1 centimeter. It's very, very close to 1 centimeter. 0.97. Okay? It will sag 0.9, I forget what it said there. I think it was 0.97 centimeters. 2 meters from the end. Obviously, neatness is not important here. Okay. Is there another distance from the end that would give you the exact same answer as you got for 2 meters? If so, what would that distance be? Okay. Remember, it was this exact spot here. Okay? 0.97. So let's go across until we see 0.97 again. We're getting really close here. I saw it. Oh man. You know, I'm just going to say we've got very, very close to the right answer here. Would you agree it's about 6.6 or 6.7 meters if we round that off? Let's say 6.7 meters, okay? Wow. Okay, about 6.7 meters. Good. At 6.7 meters on the beam, we would get the same sag. I apologize. You have to sit and watch me write this. I'm trying to demonstrate the thing that nobody likes to do, which is write sentences in math. So I'm trying to be good about it. So thank you for your patience watching me do that. Okay, so that was that question. We've got another question here. We're moving on to windsurfing. Ooh, that sounds exciting. Although working on engines is exciting too, so let's not be biased. Whoa, I'm drawing on the page. There we go. A windsurfer is sailing on the water. Fun. Her distance from the shore is d meters, and the time t is measured in seconds. Here's the formula. Okay, so d is going to be our meters. We're going to call that y when we put this in Desmos. And the x value is going to be time measured in seconds. So t is time measured in seconds. Okay, so let's quickly type this into Desmos right now. Let's get our equation editor back. And you can click the little x here to get rid of it. And what is the equation? Y equals 0.002. Y equals 0.002 x cubed. You already know how to do that cubed. In fact, I'm not going to try and talk too much while I'm typing it in because I'm sure you can do it. Plus 0.04 x squared. Plus 0.04 x squared. I can push the a squared button there. It's quicker. Next is plus 0.3x. 0.3x. Okay, we now have our situation. I'm going to get rid of this so we can see things better. Again, just like in real life, we usually start when time is 0. Because remember, the x values are time. Okay, so here's 0, here's 1 second, 2 seconds, 3 seconds. And these values up here, it said, was the windsurfer's distance from the shore. So the windsurfer was windsurfing and moving away from the shore. Okay? And if we zoom out, we see it gets quicker and quicker. The line is not straight. She's moving at an exponential rate. An exponential graph is a graph that does, grow in this direction. So so we graphed it. Good. The x-axis is referring to we just talked about this, the time in seconds. And the y-axis is referring to the distance from shore. Thank you for your patience. What domain makes sense in this situation? Well, x has to be, or time has to be greater than 0, okay? Because you start the clock and it starts moving in this direction. So we don't really know how long she's out there. So I guess we can just say it goes forever to the right. Otherwise you could say, well, she's not going to windsurf forever. But I'm just going to write it out where the domain is x such that, x is an element of the reals such that x, or time, must be greater than or equal to 0. Okay, it's kind of going on forever. But I'm sure in real life, she's going to need to stop, come back to the shore, use the washroom. Unless she did that in the ocean, but that's her choice. And I apologize for that. Or to come back and eat a picnic lunch on the beach, which is also a fantastic idea. Okay, let's move on. What is the distance traveled by the windsurfer from the shore in 10 seconds? That's a nice question. 10 seconds. Okay, I don't see this x-axis going up to 10 here. So the nice thing about Desmos, you just move it over or just zoom out. Okay, at 10 seconds, we can see the graph goes right to this spot right here. She is going to be 9, what is that, meters from the shore? After 10 seconds, she'll be 9 meters. Let's go back and see. Yes, it is meters. Okay? So she will be 9 meters from the shore. Again, a word answer. She will be 9 meters from the shore at 10 seconds. What a nice demonstration of a word answer. Okay, when will the windsurfer have traveled 38 meters from the shore? Oh, okay. So they want us to look and see the y values when that is 38 meters. So let's zoom out here. Okay, 38 meters, wow. What you can do is kind of drag your mouse along here, or your finger if you're using a tablet. And we want 38 meters. We're almost there, we're at 37.8. Oh, I saw it there for a second. Did you? Wow, you could probably just push pause on your video, but here we go. Remember this, folks. It was 20 seconds when she was 38 meters from the shore. Okay, I'm letting go of the mouse and it disappears. Did you remember what it said? She was 20, whoops, not she was, I'm saying that wrong. It took 20 seconds to reach 38 meters from the shore. Okay, hopefully you saw that Desmos is so nice and it's so much easier than trying to draw that stuff out on paper. Not that that's a bad thing, but I'm just showing you Desmos is really nice to use when you have to do questions like this and you're allowed to use technology. It's far nicer than any other graphing calculator I have seen. You're welcome, Desmos, but you guys are good people. You deserve it. They gave us this calculator and the app for free. Okay, take care of people.